All right, so let's get the session started. This is a session on leakage, and I recently moved into an apartment that had a leakage problem in the roof, so I'm now acutely interested in leakage. So Yuval's going to begin the session talking about leakage tolerant circuits.
Okay, thanks Henry for the funny introduction. So before I dive into a long introduction to put our results in context, let me tell you the short version. So this talk is about leakage tolerant circuits, which are randomized Boolean circuits that provide the best possible security guarantees against simple kinds of leakage. I'll tell you about some first of their kind feasibility results, applications, and open questions. Okay, so a dream goal in cryptography is to implement general computations that involve secrets while providing the same level of security as an ideal black box implementation, even in the presence of partial information leakage about intermediate values in the computation on the left. So a popular model that formalizes this goal is that of a stateful leakage resilient circuit. Here we have an actual implementation that has a memory storing a secret state. And this green Boolean circuit that does two things. It takes an input, computes an output based on the input and the secret state, and also updates the state. So you can think of an AES circuit where the secret state is some encoded AES key. The input is a message, the output is a ciphertext. Okay, and the update function refreshes the secret key. So when we consider security here, we need to specify a class L of leakage functions, which in this talk will always output T bits. Okay, and specifically every leakage function in this class takes all intermediate values of the computation, including both the secret state and the Boolean circuit, and outputs T bits that are limited in some way. Okay, we'll talk about different leakage classes in this talk. And more concretely, we consider an adversary that can adaptively attack the system, where in each round, the adversary can pick an input, a leakage function from the class, and observe both the legitimate output, say AES ciphertext, and this partial information output by the leakage function. So we want to be secure against adversaries that can attack this system in multiple rounds, adaptively choosing inputs and leakage functions. And to formalize this, we have this notion of a leakage resilient stateful circuit compiler that takes this ideal specification of what we want to realize, maps it into a leakage resilient circuit C hat, along with an encoded initial state S0 hat. And we want the implementation on the right to be functionally equivalent to the one on the left. Again, this is a reactive functionality that takes multiple rounds of inputs. And the security guarantee is the natural simulation-based definition. We want it to be the case that the view of every adversary that attacks the implementation on the right can be simulated given an ideal access to the functionality on the left. Okay, and this is really at least the theoretical version of what we want a general purpose computer to provide us in terms of leakage resilience. Okay, so to fully specify the problem, we need to say what kinds of leakage classes L we consider, whether we want information theoretic or computational security, and also what kind of components do we allow in our implementation. Do we only want, do we want to have just a Boolean circuit with standard gates, or do we allow bigger leak-free components? And in this talk, we will focus on the most stringent setting of information theoretic security and the implementation that consists of standard Boolean circuits over standard gates. Okay, no leak-free components that have been used in some of these works. And if we look at past work on the topic, there is quite a lot of works on this and related models. And we had two-phase transitions. It started from essentially nobody being interested in this to the theory community being interested in exploring feasibility results for such leakage-resilient circuits. And then it gradually shifted to the applied community, mostly in the chess community. People are really interested in getting better concrete efficiency for such leakage-resilient implementations. And almost all of these recent works target the simplest class of leakage functions, which are local probing leakage. So here, the leakage just outputs the values of T physical wires of the circuit. And you can directly motivate it by probing attacks, but maybe more realistically, by other types of practical leakage, which this probing resilience implies, and we'll hear about this in the last talk of this session. Okay, so even though probing resilience does give us some meaningful guarantee, it is still very far from being universal. And so we can ask, what kind of global leakage functions can we protect against? And at least in the theory literature, we know something, but not a lot. So we have provable constructions that resist AC0 leakage, constant depth Boolean circuits, or so-called only computation leakage, which means that the computation is broken into many components, and every component, or many sub-computations, each of which leak separately. So this captures the main theoretical feasibility results in this area. But for these general leakage classes, and even for the simple cases where you just leak the or the parity of subsets of wires, the constructions are more complicated, have a big overhead that scales quadratically with this leakage parameter T. And the constructions are very specialized. We do not know how to apply general purpose secure computation techniques that we can apply in the easier case of probing leakage. So there is a big gap between what we can do for probing leakage and what we can do even for very simple kinds of global leakage functions. Okay, so this is sort of the motivation for this work. And so in an attempt to close the gap, let's simplify the model. And this is another type of leakage-resilient circuits that have been considered in the literature. It often serves as a stepping stone towards the previous stateful model. Here we do not have a state, but we do have a leak-free input encoder and output decoder that help us. And the security guarantee we want to achieve is very simple. We want to have this mapping C hat, which is a Boolean circuit, a randomized Boolean circuit mapping the encoded input X hat to an encoded output Y hat, such that if you apply any leakage from the class to the wires of C hat, you learn essentially nothing about the input. Okay, so here the input and output are protected, and we can expect to get this strong form of leakage resilience of revealing nothing. And to avoid trivialities, we typically want these trusted components to be small and universal. Okay, this is necessary both for non-triviality and for usefulness of this model. Okay, and you know, in this simpler model, we have much better constructions, both in terms of feasibility and efficiency. Okay, so again, this begs the question, and this applies to general leakage classes. So here's another gap we want to bridge. Can we bridge the gap between the stateless model and the stateful model? Okay, so a natural approach is to try and bootstrap from the stateless model to the stateful model. Okay, can we take any construction in the stateless model and convert it to a similar construction with similar efficiency in the stateful model? And here one encounters several barriers. First, there's a technical barrier of how do we implement these leak-free components, but even if we somehow manage to do it, there is still the issue of composability. So this simple stateless model does not compose. So if you try to iterate, right, you map one encoded state to the next encoded state and then to the next encoded state, security may totally break down. And this motivated a lot of work, especially in the applied research community, about getting concretely efficient composable notions of leakage resilient circuits, but this body of work focused entirely on the case of probing leakage, and for global leakage classes, we basically know nothing. Okay, and now this finally brings me to the topic of the talk, which is leakage-tolerant circuits. A leakage-tolerant circuit is just a circuit that maps an unprotected X to an unprotected output Y in a way that gives us the best security we can hope for against the class L. And what it means is that if we apply any function from our leakage class to the entire computation transcript, so to all wires of C hat, what we see can be simulated by applying another, possibly a random choice of leakage function from the same class only to the input X and the output Y. In other words, our implementation is as secure as a black box implementation, because also in a black box implementation, we can leak partial information about the input and output if they are not protected. Okay, so this intuitively gives us composable guarantees, and indeed, we'll see this soon. And this notion has not been systematically studied, so there have been works on this notion in the computational setting in the context of zero knowledge and secure computation. And it has been observed that constructions against probing leakage do satisfy this notion of leakage tolerance. But in terms of global leakage classes, we know essentially nothing, and this is really the gap that this work attempts to fill. Okay, so again, we have this notion which can be thought of as the best possible, and if we realize this notion, then we have something that's as good as an ideal leak-free implementation. Okay, to get a bit of intuition, let's see two simple examples. This is the first example where we take the end of the two input bits and XOR it with the third input bit. And on the right, we have the natural circuit implementation of this function. Is this leakage tolerant against a single bit of parity leakage? Okay, so parity leakage can take any subset of the wires and return their exclusive OR. So the only problematic wire here, because in the ideal model we can take parities of inputs and outputs, the only thing we should worry about is the intermediate value, the end of the first two input bits. But because this value can be expressed as the output XORed with the third input bits, we can perfectly simulate this wire and any parity of wires by parity of inputs and outputs. Okay, so this implementation happens to be leakage tolerant for parities. If we look at only a slightly more complicated example, here we take the inner product, the mod 2 inner product of two vectors of length 2. As you might guess, this is not a leakage tolerant implementation, because now the end of the first two input bits cannot be written as a parity of inputs and outputs, and in fact, it's not hard to prove that you cannot even simulate it by taking some mixture of parities, okay? So this is an example that shows us that, yes, even for very simple functions, the straightforward implementation is not leakage tolerant. Note that it's not clear a priori, right? Because the notion of leakage tolerance is not monotone with respect to the power of the class. If you consider the class of all functions, then everything is leakage tolerant, okay? But yeah, but we will need randomness, and with randomness, we can hope at least to realize every function in a leakage-tolerant way. Okay, so just to place this primitive leakage-tolerant circuits with respect to the previous primitive, which was a stateless leakage-resilient circuit, note that if we can generally convert every circuit into a leakage-tolerant circuit, then it's easy to get also a stateless leakage-resilient circuit with a trusted encoder and decoder. And the idea is very simple. We just need to take any encoding, probabilistic encoding, that is resilient to our leakage class. We use the trusted encoder to encode the input. And now we use a leakage-tolerant implementation for the function that first decodes the encoded input, now applies our computation, and then re-encodes it using fresh randomness. Okay, and now we can apply the final decoder. So if you just look at the blue part and pretend that it is implemented by ideal leak-free hardware, then it's clear that this works because all the leakage can do is apply to the encoded input and encoded output, which are protected by the leakage resilient encoding. Okay, so this shows us that leakage tolerance is morally harder to achieve, or at least as hard to achieve as stateless leakage resilience. Okay, and one might wonder, can we take existing constructions? I already mentioned that there are many existing constructions of stateless leakage resilient circuits that have attractive efficiency features. Can we take these constructions and say that somehow we can implement the encoder and decoder in a way that will give us leakage tolerance? This was also what we initially expected. So it turns out that in the case of local probing leakage, this is indeed the case for natural constructions from the literature, that they're almost all of them are also leakage tolerant against probing leakage. But in the case of even very simple types of global leakage, this is not the case. If you look at existing constructions, they will not necessarily provide you the stronger leakage tolerance guarantee. Okay, so let me summarize the contribution. We initiate a systematic study of this notion. We give positive results for two types of depth 1 global leakage. First is what we call a depth 1 AC0, which is just a fancy way of saying that you take either the or, every bit of the leakage is either the or the and of wires or their negations. Okay, this is what we call depth 1 AC0 leakage. And we also get a feasibility result for parity leakage, where we leak T bits, each of which is a parity of some subset of the wires. For the case of parity leakage, our construction and analysis need an unbounded simulator, or more precisely, the simulation running time is exponential in the number of bits that we leak. This caveat does not apply to the first result. We show how leakage tolerant circuits can, the composability guarantee they provide is helpful to give us a general compiler to stateful leakage resilient circuits. And one nice thing about this compiler is that it gives us efficient simulation even when the leakage tolerant circuit has an unbounded simulator, like in the case of parities. So in the context of the applications, unbounded simulator is not an issue, we can get around it. And as corollary, we get the first stateful leakage resilient circuits. This is the first model in the talk, against the same leakage classes presented here, where the overhead is subquadratic in the leakage parameter T. Okay, so the construction, let me say just a few words. The application to stateful leakage resilient circuits just follows the same blueprint that I showed earlier of using an LTC to get a stateless LRC. In each iteration, we apply a leakage tolerant circuit to the function that decodes the current state, performs the computation, and re-encodes it. And we need here the encoding to be secure against two adaptive leakage queries. This was also the case in an earlier work of Faust et al. In the context of AC0 leakage with trusted hardware components. And this primitive is easy to realize. Okay, I will not say much because I'm out of time about the actual constructions. Let me just say that a natural attempt, say, to protect against OR leakage would be to take the standard so-called ISW construction, where you use an XOR secret sharing of each value. You would expect it to be tolerant to OR leakage, but it turns out that this is not the case. And you need actually negations to simulate, even if the leakage does not use negations. So this is just an illustration of why things do not work as expected. And if we allow negations, then the ISW construction does work. I refer you to the paper for the case of parties, which is significantly more involved. And let me conclude. So we initiate a study of leakage tolerant circuits. We give positive results, applications, and there are many open questions like extending the classes of leakage and eliminating this inefficient simulation caveat for the case of parties. That's it.
Okay, so we have time for a quick question, either at the mic or in the chat, if anyone has one. Okay, I have one, if no one does. Which can you say, is it easy to see why the simulation should take 2 to the t time? Like, where does this?
Yeah, great question. So the simulator, when you have t parties, our simulator needs to find a small weight vector that is spanned by the parity queries, right? Think of every parity query as a vector. Our simulation needs to find small Hamming weight vectors that are spanned by the parity queries. We provide some limited evidence that this is necessary under the learning parity with noise assumptions, but it's still open. We do not know. We can only prove it for some toy example. We don't know even that our construction cannot be efficiently simulated.
Cool. All right, let's thank you all again. Okay. Next up, we have a paper about connecting leakage resilient secret sharing to practice, scaling trends and physical dependencies of prime field masking. And we may have the slides or we may not. Excellent. So yeah, please take it away.
Okay. Thank you very much for the introduction. So the paper I'm presenting today is a joint work with Sebastian Faus, Loïc Mazur, Maximilian Ort, and François-Xavier Stender. And the nice thing is that they are all in the room today. Okay, so just for I guess now you know what we mean when we talk about leakage resilient cryptography, but just for a very, very quick introduction. To prove security in cryptography, in general, we consider the black box model, where we assume that the adversary knows the description of the functionality, knows the input and output behavior, but it doesn't have any additional information on the intermediate values depending on the secret. In practice, side-channel attacks can happen, as you saw before, meaning that the adversary can actually get some additional information on the secret. In practice, this can be done via measuring the power consumption or the electromagnetic radiation, for example. And in theory, this is often modeled as a deterministic leakage component, for example, Hamming weight or LSB, plus some independent noise, such as, for example, Gaussian noise. And the main goal in leakage-resilient cryptography is to design functionalities that guarantee that the leakage is the least informative as possible. An important step in this direction is to consider the so-called secret sharing, or also called encoding schemes. And basically, this allows to avoid storing the secret directly and instead store some secret shares. And in particular, like this, there will be no direct leakage on the secret, but just individual leakage on each share. So in this work, we consider the simple sharing scheme, that is the additive sharing scheme, meaning that the shares are sampled at random with the only constraint that they sum up to the secret. We consider prime fields, meaning that the secret is the secret as well as the shares are all integers modulo p, and the sum is also modulo p. And as for the leakage model, in this work, we consider deterministic M-bounded leakage model, meaning that there is no noise, and the evaluation of each leakage function on each share can be represented as a binary string of fixed length M. So previous work in this topic have already shown that increasing the number of shares seems to have a positive impact in improving the leakage resilience of the scheme. And the question that we ask ourselves in this work is what is the actual impact of the field size as a parameter. So previous work actually have already considered the field size as a parameter, and in particular, Jembowski et al. And also Benamouda et al. Have provided an upper bound that concerns generic M-bounded leakage. From this upper bound, it emerges that when the amount of bits leaked, M, is constant, then it actually seems that increasing the field size does not have a significant impact on security. While when the amount of bits leaked is increasing with P, from this upper bound, it actually seems that increasing the field size can even have a negative impact. A follow-up work from Maggi et al. Has focused on the special case of LSB leakage. So each leakage function just leaks the least significant bit of each share. And in this case, they've actually confirmed the upper bound for constant number of shares, for constant number of bits leaked. And they have proven tightness up to a constant. The only limitation here is that their analysis is just for worst-case secrets. So one first question is in this direction is to understand what happens in the average case. Also, another interesting question that we consider in this work is what happens for other practical leakage models beyond the least significant bit. So our first contribution is to extend the LSB leakage analysis to average case secrets. And in this case, we actually confirm the previous results. We prove tightness also for average case. And this means basically that increasing the field size does not significantly improve security. Then we move to Hamming weight leakage, and in this case we provide an upper bound for worst case secrets. And the main reason why we consider worst case is because an upper bound for worst case also implies average case secrets. In this case, we actually go in contrast with respect to previous works, and we show that increasing the field size does improve security. Finally, we complement our theoretical results with simulated experiments concerning more generic leakage models. In particular, for intermediate linear functions between LSB and Hamming weight, we show that there is a smooth degradation. So in particular, when we take leakage functions that are close to LSB, then it seems that the impact of the field size is not significant. When we consider functions that are closer to Hamming weight, it seems that increasing the field size can be a good countermeasure for improving the leakage resilience. We also performed simulated experiments for random linear functions, and in general, we observed that increasing the field size has a positive impact on leakage resilience, but there is quite some variability, so this definitely motivates further work on the topic. So in the rest of the talk, we are actually going to focus on Hamming weight leakage. Of course, the rest of the topics are covered in the paper, and you can just feel free to ask questions about the rest in the end of this talk. Okay, so just for a smooth start, let's quickly review what we mean when we talk about Hamming weight leakage. So for every share, we consider the binary representation, and from each binary representation, we leak the sum of the bits in the binary representation. I mean, basically, the Hamming weight of each binary representation. So this is a special case of M-bounded leakage, where M increases with P, and in particular, in this case, M goes like log of log P. And the main reason why we consider Hamming weight and we say that it's a rather practical leakage model, it is because it has a correlation with the power consumption of the device. Okay, now we quickly summarize with this plot our result with respect to previous work on Hamming weight, let's say, even though it was never really about Hamming weight specifically. And in this plot, we have on the x-axis the logarithm of the field size, meaning the number of bits with which the secret and the shares are represented. And on the y-axis, we have the amount of leakage. And an additional information is that what we and prior works consider is a normalized or almost normalized metric. So we only care about the values that are below 1. Only those are actually informative. In this figure in particular, we fix the number of shares to 6, but our work actually covers more shares. Okay, so what you see in orange is an upper bound from prior work, in particular from Benhamouda et al. And this upper bound holds in general for M-bounded leakage, but in this case we display it for the number of bits leaked from the Hamming weight leakage function, so log of log P. What you can observe from here is that in general there is an increasing trend. It can be observed. And since the metric is normalized, actually we can see that not many values are actually informative, at least for this D. And to have informative values for larger P, we would need to take a greater number of shares in general. What you see in blue is a numerical computation. So there are not so many values here. It was quite computationally intensive. But what you can observe is that the trend is quite different from the one for generic unbounded leakage functions. It is decreasing, and it seems that the leakage is way less informative. And what you see in pink there is our own upper bound. Test? Oh, yes, now it works. Thank you. Yes, so yes, in pink, our upper bound. You can show that the upper bound actually reveals a decreasing trend with the field size. In particular, our upper bound goes to 0, like the logarithm of the field size, elevated to 1 minus d divided by 4. And in particular, this means that increasing the field size improves leakage resilience as long as we take at least 5 shares. Okay, so in the rest of this talk, I'm just going to give you some intuitions on what are the main techniques that we use to get this bound. So similar to prior work in the field, we study leakage resilience secret sharing via Fourier analysis. And now I will just give you a very rough intuition on why this is such a popular technique. So in linear secret sharing, the secret is a sum of random variables, namely the shares or constant multiplications of shares after leakage. And in probability theory, the sum of random variables has a distribution that under some independence assumptions can be represented as a convolution of the individual distributions of the shares. And as was actually mentioned already in a talk today, the Fourier transform has the main advantage that it transforms the complicated operation of convolution into multiplication. So it's let's say, it's a good technique to deal with convolutions in general. So in line with this intuition, Benamouda et al. Actually proved that in order to upper bound the leakage resilience of the scheme, in a given leakage model, it's enough to actually upper bound the maximum amplitude of the Fourier spectrum corresponding to that model. So just to give you a graphical picture of what we are talking about, like these are two Fourier spectrums. The one in blue is the one for the Hamming weight, and the one in orange is for the LSB. Let's say in this part of the talk, we are going to speak about how we maximize the, let's say we upper bound the maximum Fourier coefficient. So our first step in this direction is to consider a normalizing condition for Fourier coefficients. In this case, we consider Parseval equality. That basically says that the sum of squared Fourier coefficients equals a constant. So the interesting fact is that Parseval itself would be already enough to get an upper bound, as the maximum Fourier coefficient is actually a summand. So we can always upper bound a summand with the whole sum, right? But in our work, we try to make this upper bound a bit more fine-grained. And we do it by looking for patterns within the summands. And in particular, what we prove is that every Fourier coefficient has at least 2n copies within the sum. This comes at the price of an additional assumption, that is that the prime field in which we operate is actually, the size is actually a Mersenne prime, meaning that it equals 2 to the n minus 1, where n is the integer that then defines the number of copies. And this property comes from two main observations that are actually inherent of Mersenne prime fields. So the first one is that for every field element alpha, we can get the binary representation of p minus alpha by bitwise flipping the bits in the binary representation of alpha. And the second property is that for every field element alpha, we can get the binary representation of 2 alpha by just shifting the binary representation of alpha one step to the left. And iterating this step, we can get also 2 to the k alpha for every k smaller than n. So this property allows us to save a factor square root to the 2n, which is actually the factor that allows us to say that the trend is decreasing with respect to the field size, because then the upper bound is inversely proportional to n, and n goes like the logarithm of the field size. Okay, so just to conclude the talk, a summary of our main contributions. Our first result is an extension of the LSB analysis from Maggi et al. To also include average case secrets. And in particular, we confirm that larger fields do not seem to improve leakage resilience against LSB leakage. Our second result concerns an Hamming weight analysis, and in this case, we actually proved that taking larger fields does improve leakage resilience, and therefore it makes sense to consider it as a countermeasure. Our third result concerns simulated experiments for more general but still practical leakage models. For intermediate leakage models between Hamming weight and LSB, we show that there is a smooth degradation in increasing the field size for improving security. And for random linear function, we show that in general we have a good incentive in increasing the field size for improving security, but there is quite some variability. So therefore, one interesting open problem is to extend our results to also formally cover the simulated the models for which we just have simulated experiments. Another interesting open problem is to combine our analysis with the study of noise as well, because our analysis only considers deterministic leakage, and therefore it would be interesting to understand how the whole thing also scales with noise. And one last interesting open problem is to consider more complex gadgets, meaning what happens when we do compute on the shares. So how it works then with the leakage resilience of the whole functionality. So this is all from my talk. Thank you very much for listening.
Great, so questions for Elena, either up at the mic here or in the chat? So can I ask a question?
Yeah, sure.
I was curious, on the slide before the last one, you were saying you needed this restriction that p-1 is the power of 2.
Yes.
I was wondering, how much can you relax that? Could p-1, if it's a product of small primes, or 3 to the n, or what else could you do there?
Yes, so this we haven't really checked. So actually we also simulated numerically what can happen with different primes, and we anyway observed some decreasing trend. But our techniques are quite inherent to this model for primes. But I'm pretty confident that this can be relaxed.
Cool. One more question? All right, if not, let's thank Elena again.
Thank you very much.
All right, next up is Gianluca Bryan from ETH here in Zurich, and he's going to be speaking about going from random probing to noisy leakage without dependence on the field size.
Thank you for the introduction. So, hi everyone. This is joint work with Stefan Jambowski and Sebastian Faust. At this point, you're already quite familiar with side channel attacks, so I'll try to be as fast as possible. You have a cryptographic algorithm. You prove that this is secure. Then you go to implement this in software or in hardware, and you discover that the adversary, the attacker, could learn some additional information and make that the algorithm or the circuit not secure anymore by exploiting physical phenomena like the power consumption or the running time of the device. So in order to protect against this kind of attacks, we have to first define the model of computation and the leakage model. We start by the model of computation. We model computation by using circuits. In particular, the input will be the input values on the input wires. Then we apply every gate to get the intermediate wires up until the end of the circuit. And we finally get the computation of the function, and this will be the circuit that implements this particular function. So this is a quite general model, because in this case, this is a Boolean circuit, but we can extend it to have any kind of gates. In particular, we could also simulate software with that, in which gates are CPU instructions. In our case, we are in the arithmetic circuit model, in which computation happens in a finite field F, and we consider 3 kinds of gates: addition, subtraction, and multiplication gates. And we consider 2 additional kinds of gates that are for technical purposes. One is the copy gate, which splits a wire into 2 different wires carrying the same value. And the other kind of gate is the random gate that outputs a fresh and uniform random value in the field. So speaking about the leakage models, there are many leakage models. The first one of the first leakage models was the one from Ishai, Sai, and Wagner in 2003, in which they formalized leakage by the use of probings. In particular, every probe will output some value on some of the wires of the circuit. So this is quite simple. But does not capture realistic situations like the noisy leakage one, which is on one side more realistic. Noisy leakage captures the fact that, for instance, that the attacker could gather a lot of data and extract a small information from this data. However, noisy leakages are difficult to achieve in practices. Like security against noisy leakage is difficult to achieve in practice. So this is why intermediate models came up, and in this work we are focusing on random probing and average probing. So random probing is very similar to threshold probing, except that now the adversary is able to leak from every single value of the circuit, but there is a catch, because otherwise it would be impossible to protect against. And the catch is that the random probing function only outputs the value on the wire with a certain probability epsilon, and outputs nothing with probability 1 minus epsilon. So this is a nice model, but in 2015, Jambowski, Faust, and Skorsky came up with a stronger model, which they call average probing, which says that the exact same thing of random probing, but in this case, the probability of leakage is for a uniform random variable of the wire, but the actual leakage probability from the wires depend on the value that are on the wires. So this reveals more information, because now, even if the wire does not leak any information, this still reveals some information about the distribution that is on the wire. So why did they come up with this new model? So first of all, in 2014, Duke, Jambowski, and Faust proved a nice relation between the threshold probing and random probing, and more importantly, they proved a nice relation between random probing and noisy leakage. In particular, they proved that any epsilon random probing secure circuit is also epsilon over size of the field noisy leakage circuit when measured with the metric of statistical distance. This is, of course, nice, because now proving that a circuit is secure in the random probing setting is equivalent to prove the circuit secure in the more powerful noisy leakage setting. However, they incur in this loss of the size of the in terms of the size of the field. So if the field is large, then this is not as good as it could be. So in 2015, Jambowski, Faust, and Skorsky came up with the average probing model, and realized that with the average probing model, they are able to achieve a tight reduction. So a delta average probing secure circuit is also a delta noisy leakage resilient circuit in the statistical distance setting. They also proved a nice, that this also works in the other way around, with a loss of a factor of just 2. So our work takes place in this setting, and what we do is construct a compiler that compiles random probing secure circuits into average probing secure circuits, and we get a parameter of epsilon squared instead of epsilon over size of the field, which is good because now we are not depending on the size of the field anymore. And finally, by applying the result from Jambowski, Faust, and Skorsky, we are able to directly compile circuits from random probing to noisy leakage. So how do we do this? First of all, we have to define the simulation paradigm. We have the original circuit on the right, the compiled circuit or transformed circuit on the left. we get some leakage information from both circuits. We give a name to these two random variables, and we say that the leakage from the transformed circuit is simulatable from the leakage from the original circuit if there exists a simulator that is able to output the same distribution as the transformed circuit leakage by only receiving as input the original circuit leakage. And now we are able to achieve security because it suffices to prove that if the original circuit is random probing secure and the transformed circuit has simulatable leakage, then the transformed circuit is secure in the target leakage model, which is average probing. Okay, so how does our compiler work? We use the very common model of masking. In particular, we convert every wire into a bundle of, in this case, 2 wires. And the bundle carries an encoding, which is an additive secret sharing. So the sum of the 2 wires gives back the original value on the original circuit. And we also have to come up with gadgets that compute the equivalent of the original gates, but on encodings instead of single wires. And we prove security using a standard hybrid argument. So we start from distribution of the real leakage from the circuit, and then we replace the leakage from the last gadget with simulated leakage from that gadget. And then we do this for the second to last gadget, and so on, until eventually all the leakage from all the gadgets are replaced with simulated leakage. And now what happens is that the leakage from this circuit is completely simulated by simulators that only get as input the leakage information from the original circuit and nothing more. So we can define the circuit simulator in this way. Okay, this is fine, this is nice and fine, but there is still one problem, that we need composable gadgets that work well and a way to compose the simulators. So how do we want to define the simulator? In theory, we want that the simulator outputs the same distribution of the real leakage. However, and we want to give the simulator just the random probing leakage from the original circuit. However, this is a problem because now the simulator could be inconsistent with the values that are previously in the circuit. So we do a slight modification, and we give if the original value leaks, then we give the full input encoding to the simulator, and this allows the simulator to correctly simulate the leakage distribution. And if the original wire does not leak, then we give nothing to the simulator. So in particular, we will see that the simulator simulates that no values leaked. So this was an example for simple gates with 1 input and 1 output wires, how to extend the result for gates with more than one input wire. We simply do the same for every possible wires, and we say we give the simulator all the information if all the wires leaked, and we give no information at all to the simulator if at least some of the wires didn't leak. Okay, now we are ready to define what should be the distribution of the simulator. So in particular, this is what we want to achieve. We rewrite this in terms of probability, and we split this into the 2 cases in which we give the actual input information to the simulator, which happens with probability epsilon because of the epsilon random probing, and the situation in which we give nothing to the simulator, which happens with probability 1 minus epsilon. And now we can proceed by case distinction. In the first case, lambda different from bottom means that at least some of the wires leaked from the gadget. So in this case, we play safe and we say that the simulator, when receives nothing, outputs nothing. So the probability that it outputs something is 0. And this is because, again, otherwise the simulator could produce some internal values in the gadget that may be inconsistent with the rest of the circuit. In this case, we just rewrite the above equality and it becomes simple. This is just a rescaled version of the original leakage, of the actual leakage. And this rescaled version takes into account the fact that that comes from the epsilon random probing. The second case is a bit more involved because we still rewrite the above equality in this other way. So we get the probability that the simulator with the actual input information outputs nothing. But we have to be careful here, and because in particular, this is a probability distribution, and we have that this must be greater than or equal to 0. So this is how we define the distribution of the simulator. And we have to take care of this last constraint. And we realize that this happens whenever this distribution, the distribution of something leaks from the gadget is bounded by epsilon. So this means that if the probability that something leaks from the gadget is less than or equal to epsilon, we can simulate. What happens if we switch from the situation of one input wire to 2 input wires? We are only considering gates with at most 2 input wires, so this is fine. With 2 input wires, the simulator has to get the information of both the input wires, so the probability to get both information is epsilon squared now. What we do is just replace every epsilon we see with epsilon squared, and the final constraint that we get is that the real leakage is upper, like the fact that something leaks in the real gadget is upper bounded by epsilon squared. So this is why we get this slightly ugly bound. So these are our gadgets. They are quite simple, and the most complex gadget is the multiplication gadget. And for the multiplication gadget, we have a bound that the probability that something leaks from the gadget is upper bounded by 35 delta, where delta is the parameter for the average probing. So we can put that 35 delta into the simulation condition, and we get that 35 delta, whenever 35 delta is less than or equal to epsilon squared, then we are able to simulate, and we are able to achieve the main theorem that there exists a circuit compiler that compiles epsilon random probing secure circuits into epsilon squared divided by 35 average probing secure circuits. By using the result from Jembowski, Faust, and Skorsky, we can directly apply this and get a corollary in which we compile epsilon random probing secure circuits into epsilon squared over 35 statistical distance noisy leakage resilient circuits. So that was all. This is a summary of our results. Again, we construct this compiler from epsilon random probing to epsilon squared. This epsilon squared is a bit ugly, so we leave it as an open problem to do better, to, for instance, get rid of this epsilon squared and hopefully get something that is just epsilon. And we also leave 2 other open problems. The first one is whether it is possible to extend this result to the more general types of circuits. For instance, circuits that compute arithmetic circuits over rings instead of fields, and this would be useful, for instance, in the post-quantum setting. And another open problem is whether the same technique can be used to achieve other interesting results in the setting of private circuits. So that is all, and thank you for your attention.
So questions? I'm hoping for at least one question from the audience in this session. You're going to make me do it again. Really? Okay. So I'm curious, at the very end here, you mentioned the post-quantum setting.
Yeah.
So has anyone looked at, I mean, you could ask the same question for quantum circuits. Does this even make sense, or is this something that people have thought about?
For quantum circuits, I don't know. The thing is that maybe I said quantum, maybe I meant post-quantum, sorry. But yeah, the thing is that in the post-quantum setting, usually operations happen in rings that are, for instance, Z modulo, something which is not necessarily a prime. And in this case, like probably the result still applies, but something has to be modified because there are some technicalities in, like, let's say that a field is simpler to work with because there is only one element that is 0 that is problematic in some way, and everything else is fine.
There is an additional problem in post-quantum, and this is that any leakage which is measured is going to influence the circuit itself. This is something which is not included in our
But I guess the question is, does that make it sort of trivial? Does that trivialize the problem, or is there still anything to say, I guess? Yeah. All right. Well, let's thank Gianluca again. And we have a track switch break until 3:05.